Hey guys, I'm gonna go over the 8.7, 8.8 homework. I know you guys have been waiting on this one. Let's jump into it. So we're talking about solids with cross sections. So finding volume of solids with cross sections. So it tells us that the base of the solid is the region in the first quadrant bounded by the graph of 1 minus x to x divided by 3, which if you kind of rewrite this, you can think about it as as negative 1/3 x plus 1. Might make it easier to kind of draw a sketch of this region. So this region in the first quadrant, and it's bounded by this graph right here. It has a y-intercept of 1, and it's got a slope of negative 1/3. So that would mean that if I count this down to the x-axis, it would be down 1 and over 3. So this is y equals 1. This is x equals 3. So our region is this triangular region right here. So that's our region, and this is what the base is on top of. So if you imagine this, just this the quadrant on a flat plane. Let's see, I'm really not that good at drawing it from an angle, but say that this is the I don't even know what I'm saying. So let's look at it from a different angle. So this is the region right here. And then continuing on, the solid, for the solid, each cross-section perpendicular to the x-axis is a square. And so if I were to take a random cross-section here, or I guess I could say here, it's going to be a square cross-section. So it's a square cross-section anywhere you take anywhere you take the cross-section. It can be even over here, but you can see that kind of as I don't know how good that is, or if you guys can even really make sense of what's happening right there, but maybe if I draw a square. Trying to draw 3D is so hard. Let's see. I don't even know how I would draw this. So going out here, make a triangle like that. Although maybe I should do it like, I got an idea. I'm gonna take way too long on this video, mainly because I'm gonna be drawing a bunch of stuff. Like that. Oh my gosh, this is actually turning out pretty good. So this is pretty much what we're trying to find the volume of. This is the base. It's that the base is like this right here. We got square cross sections. This is the front of, you can say that this little surface area right here is the front. But if I take any sort of random cross section in the middle, like what I'm doing here, then we're gonna add up all the cross sections. All right, that took way too long, but it was kind of fun. All right, so what is the volume of this solid that's being described right here? Well, so I know that the side, so let's say this side right here, which is also the side that I'm taking right here, that side right there is the length of, well, it's just the function itself. So this side is 1 minus x over 3. And then the area of a side is equal to the area of a square is the side squared. And then to find the volume would be equal to the integral. In this case, we're going to integrate from 0 to 3. That's the length of our region and of the area. Okay, and so, yeah, let's go ahead and integrate this right here. Now you're going to have to FOIL that right there. So 1 minus x over 3 times by 1 minus x over 3. So when I FOIL that, I'm going to get 1 minus 2/3 x plus x squared over 9 dx. And then find the antiderivative. That's going to give you x minus, well, that's going to have to be x squared. We're also going to have to divide by 2. That would make it 2/6. So that should make it 1/3. So 1/3. Yep. And then plus, and then I'm going to have to add 3 to that and divide by 3. So that would make that, we have x to the third and 1/27th, I think should be it, from 0 to 3. The only thing we have to plug in is 3. So if I plug in 3, I'll get 3 minus 1/3 times by 9 plus, well, that's just going to become 27 over 27. So that's going to be equal to 3 minus 3 plus 1, so comes out to be 1. So the volume of this shape will be 1. All right, we got a calculator one. All right, so the base of the solid is the region in the first quadrant bounded by, yet again, another linear type function. So if I go ahead and graph that right there, so we're going to have 2 minus 2/3 x, so that means we're going to have a y-intercept at 2. If I go down 2 and over 3, it's almost identical. It's very similar to this one right here. And the x-axis and the y-axis from x equals 0 to 3. For each solid, each cross-section is perpendicular to the y-axis. So that's different from here when it was perpendicular to the x-axis. That means that these cross-sections aren't going to happen in the direction where they're perpendicular to the y-axis. They're going to happen in the direction that they are perpendicular to the y-axis. So yeah, not perpendicular to the x, perpendicular to the y. So my cross sections are now going this way right here. So if I were to try and redraw this right here, so basically I have the same shape right here. This is no longer where the side is going to be though. So in this case though, the cross sections are now going this way, if that makes sense. So say I make a square out of this side right now. Then I draw it from here and then from there. Man, it's so crazy how a dashed line kind of changes things. Weird. But yeah, so this would be the front of it right here. So kind of like if I were to draw it right here, it would be from there. Anyways, try drawing them yourself and see if you can get an idea. But this is the base right here. So that's what this base is right here. And you can see that these cross sections are perpendicular to the y. So this would be the y-axis. This would be the x-axis. But yeah. So going back to this right here. Now the side is right here. And for that side, we have to redefine the curve to be in terms of y, not in terms of x. So I'm going to add 2/3 x and subtract y. And then I'm going to multiply by 3/2. So I'll get x is equal to, so 3/2 times by 2 is just going to be 3. And then minus 3/2 y. Yeah. Okay, and so that's what this side is right there. And then that means that the area is a of y. is going to be equal to 3 minus 3 halves y squared. So that means the volume, now for the volume, we have to integrate from 0 to 2. And then we're going to have our area, 3 minus... Oh, wait a minute. I didn't even read the problem all the way. It's a rectangle, not a square. Rectangle whose height is 5 times. Okay, well, that's okay. That just means that this is supposed to be longer, but whatever. Alright, so backing up just a bit. So if this is what the side is equal to, okay, so that this is the side, the height is going to be 5 times the width. And so in that case, we would say that the area, A of y, would be equal to 5 times by side squared. Since, so 3 minus 3 over 2y squared. So squared because it's still a square, just, well, it's not, but you're still using the side, but one side is 5 times larger. So 5s for one side times by s for the other side to get 5s squared. That's what we want to do. So we're going to do volume is equal to the integral from 0 to 2, 5 times by 3 minus 3 halves y squared dy. So I'm going to use my calculator. If you guys don't have a calculator, just pull up in Desmos, and if you type in int into Desmos, it will give you an integral, and then just type this in right here, and that should do it for you. So I'm going to do from 0 to 2 x excuse me, and then 5, 3 minus 3 halves, I'm just going to do x, and then I'm going to square that, and I got 30 as my answer. Alright, let's try another one, another calculator one. So let R be the region in the first quadrant bounded by the graphs of x cubed and 4x as shown in the figure above. The region R is the base of the solid. For each solid, each cross-section is perpendicular to the y-axis. So that would be this way right here. So it has to run perpendicular to the y-axis. Okay, so let's take a random cross-section. Now let's also measure this distance right here. So let's give this side. Now this side right here would be, so you'd have to take the distance from here to here, which we know to be y equals x cubed. And then we would have to subtract this distance right here, which we know y is equal to 4x. But because we're running perpendicular to the y-axis, let's solve these for y. And so rather than saying y is equal to x cubed, we'll say x is equal to the cube root of y. And then we'll say that x is equal to y divided by 4. So that's what we want for those. That means this side right here is equal to the cube root of y minus y over 4. And each cross section is a square. So that means that for the area A of y will be equal to, I'll just say y to the 1/3 minus y over 4. And then for the volume, oh wait, that has to be squared. And for the volume, we do the integral from 0 to 8 in terms of y. So from 0 to 8 of A of y, which I have defined up here, dy. And again, I'm going to punch this into my calculator. So 0 to 8. And then we're going to have x raised to the 1/3 minus divided by 4, and then that's going to be squared. And I got 2.438, so I got B. Alright, so for 4, let R be the region in the first quadrant, bounded by the graphs of x squared. So it's making me draw it this time. So, so x squared, and so that would be like this right here, and the line x equals 4. So we'll say that this right here is x equals 4 in the x-axis. So that would make this right here our region. Oops. So this would be our region. R is the base of the solid whose cross-sections are perpendicular to the x. And so this is the region R. The cross-sections on region R are perpendicular to the x-axis. Okay. And they're equilateral triangles. I kind of want to try and draw this, if you guys don't mind. I'm going to give it a shot. You guys can skip past my drawing if you want. Let's see. So I got my x and my y-axis. I'm going to have my parabola, which is going to do this right here. I'm going to have my line at x equals 4. And I have my region right here. Okay, so far so good. We're going to take a cross section. Cross section runs like this, and it's going to be an equilateral triangle. So there's one. The furthest most right, oh man, I don't know if I can do this. Would be like that right there. And it would like curve up like this right here. Yeah, let me try and draw it. So I'm going to try and draw it without all the other lines, the graph. So the region is going to have to, the base is going to have to run like this and like this right here. Okay. So this is the base right here. Let's see if I can make it decent enough. I'm going to replace that with a red line. Decent enough equilateral triangle. Is that a decent enough equilateral triangle? And oh man, it's gonna have to like make like some sort of curve like that. Yeah, something like that. Really, really funky kind of a shape. Here, I gotta make that one actually gotta make that a dotted line, you know, for the effect. Make it blue. Yeah, like that. So weird. And then anytime you make a cross section, different cross section, so measuring it from there to there, from there to there, there's another little cross section somewhere in between them. Yeah. Cool. That was fun. All right, now let's get back to the actual problem. All right, so if you guys refer to your notes, oh man, so for the notes, we said that the area of an equilateral triangle, wasn't it square root of 3/4s squared? I can find out without using it, but so let me think about this right here. If I have an equilateral triangle, call this S. This right here we'd call the height. It's a 60 angle here. That would make this a 30 angle. And then if I said that sine of 60 was equal to, this would also be sine of 60 from here, opposite over hypotenuse. So that would be h over s. And sine of 60 is root 3 over 2. that's equal to h over s. That would mean that s is equal to root 3 over, that means that height is equal to root 3 over 2, and the area of a equilateral triangle is 1/2 of its base, or the side, times by the height. That's going to be 1/2 of s times by, that should be s right there, square root of 3 over 2s, which would be square root of 3 over 4s squared. So yep, that's the area that I'm looking for. And okay, so if that's what area is, we know that the side, so this side right here, or this side right here, is just going to be x squared. So my area should be square root of 3 over 4 x to the 4th whenever I square that. So volume will be equal to the integral from 0 to 4, since we're integrating to x equals 4, and then we'll have square root of 3 over 4 x to the 4th dx, and that's going to be equal to square root of 3 over 4, and then that would be 1/5 x to the 5th, from 0 to 4, and that's going to be square root of 4 over square root of 3, square root of 3. I'm just going to keep it as 4 times 5, just because I'm looking at these numbers right here and I see a 5, so maybe the 4 will cancel, and then we're going to have times by 4 to the 5th minus 0 to the 5th. So that means that a 4 can cancel. We'd have the square root of 3 over 5 times by 4 to the 4th power, and 4 to the 4th power is 256, so I would get 256 over 5 square root of 3, so that would be B. Alright, for 5, the base of a solid in the region in the first quadrant between x cubed. I'll try not to graph this if I can help or try not to draw it if I can help myself. Okay, so x cubed, so maybe something like this right here. And the x-axis from 0 to 1. The base of the solid in the region of the first quadrant between the graph of x to the third and the x-axis from 0 to 1. Okay, so here, if we call that 1, for each solid is perpendicular to the x-axis, and it's a semicircle. So that means, well, the area of a semicircle is 1/2, or I'll say pi halves. Pi halves r squared, and r is going to be equal to half of the side, since over 2, since the radius would be, since this is a semicircle right here, the radius is in between them, and so I have to think that r is just half the distance of s, and s is equal to x to the third, so x to the third over 2, so that means a of x is equal to pi over 2 times by x to the third over 2 squared, so a of x would be equal to pi over 2 squared is 4, so pi over 8 times by x to the 6th. So for the volume, I'm going to say pi over 8 integral from 0 to 1 of x to the 6th dx, which will be equal to pi over 8 times by 1 over 7 x to the 7 from 0 to 1, which will be equal to pi over 8 times by 7, because I don't know what 8 times by 7 is off the top of my head, times by, that's all it's going to be. I think, according to the answers, that 8 times by 7 is 56. So I'm going to call it good right there. All right, the base of the solid is the region in the first quadrant. Why are these all in the first quadrant? Why not, I guess. Our first quadrant, we have 2x. Okay, that'd be x. We'll call this right here 2x. And the x-axis for 0 to 1. That's all, just from 0 to 1. So this would make this 1, 2. I don't know why that I don't know why that would be important. Unless we're integrating, we're not integrating with respect to y. So let's see. So for each solid, each cross section perpendicular to the x-axis is a quarter circle. So this is only supposed to be the cross section is supposed to be a quarter circle, and the corresponding circle center is on the x-axis. So this is the center, and the radius is in the xy plane. So, oh man, you guys are gonna have to forgive me. I'm gonna take one more crack at this one just because it's a different shape. So let's see right here, and we got 2x right here. So if we do a cross section like this right here, I'm trying to draw like an equal-ish radius. So there you go. That would be the cross section right there. We'll call this 1 right here. And then we just have to go like this, right? Oh man, that one's kind of a trickier one to draw, but we just have a triangular base. Now this would have to be twice as long right here. Since it's 2x, this would have to be twice as long as that right there. Okay. Let's see, the front of it. Oh man, I'm having a hard time with that one right there just because I can't get that angle right. And it would have to be the same since it's a center of the circle. So maybe like that. Yeah, that one looks really, really weird. I don't know if you guys can see it as well as I can, but then maybe a smaller cross section would be like this right here. Yeah. It kind of looks like it's like a, I don't know what what it looks like. All right, that's my doodle. Okay, so in any case, so since that's the radius, we can say that the radius is equal to 2x. The area of a quarter circle is pi fourth times by r squared. So that means a of x will be equal to pi fourth times by 2x squared. And I could call that pi over 4 times by 4x squared, which would just be pi x squared. And so the volume will be equal to the integral from 0 to 1 of pi x squared dx, which would be equal to pi, and then that would be 1/3 x to the third from 0 to 1, which would just be equal to pi thirds. So that would be A. All right, that should do it. Sorry I kept you waiting, and sorry I made you watch the doodles, but that should do everything for this homework.